Hello everyone, today we are going to discuss design of shaft when subjected to combined twisting and bending moments. An example of one of the shaft that are subjected to both twisting and bending moments is a propeller shaft. You find that it is, as it is turning, it is either pushed or pulled along its axis, and therefore designing it requires you to consider some principles of twisting or application of torque and bending stresses resulting into bending moments. So therefore, when a shaft is subjected to combined twisting moment and bending moment, then the shaft must be designed on the basis of two moments simultaneously, as we have already said. Various theories have been suggested to account for the elastic failure of materials when they are subjected to various types of combined stresses. And the following theories are important from the point of view. One is what we are going to call the maximum shear stress theory, or the Guest theory, or Tresca's theory, and it is used majorly for ductile materials, for example mild steel. And we have another theory called the maximum normal stress theory, or the Rankines theory, and is basically for brittle materials such as cast iron. Now in this analysis, we are going to let tau to be the shear stress induced due to the twisting moment, which we can always say is torque T. Then the bending moment sigma b, the sigma b to be the bending stress, or the stress as a result of the bending moment, which could be tensile or compressive, and is of course is always due to bending subjected to that particular part or component. Now case 1, if we are to consider the maximum shear stress theory in the shaft, it therefore states that tau max, or the maximum shear stress, is as a result of half of square root of the bending stress squared plus 4 times the square of the shear stress in the component. And from torsional theory, we have discussed that it is actually given that torque out of J, whereby J is the polar second moment of area, is equal to tau, which is the shear stress developed in the component as a result of this torque, divided by radius r, the capital R, which is the outer radius of the component. If it is a shaft, then we are talking about the outside radius, or the outer radius, equaling to g theta divided by L, whereby g is the modulus of rigidity and theta is the angle of twist, L is the length of that component if it is a shaft that we are considering. Having known that, we also have to know that the direct stress owing to bending is as a result of maximum bending moment divided by I, which is the second moment of inertia, or the second moment of area, is equal to the bending stress divided by Y, and therefore it means that sigma b is equal to bending moment m times y max divided by I, and the y max is actually the distance between the outer fiber of the distance of the outer fiber from the neutral axis. And if it is a shaft, for example a solid shaft, this y max is actually equal to d out of 2, which is equal to r. In other words, we are trying to say that the maximum stress or bending stress acts at a point, or takes place at a point which is at a distance y max from the neutral axis, and if it is a shaft, then it is at a distance equivalent to d out of 2, or the outer diameter divided by 2. Therefore, having also put that one in our mind, we also know that the second moment of area I is equal to pi divided by 64 times d to power 4. But we also know that J is equal to pi d to power 4 divided by 32. This is basically for solid shaft. These are solid shafts. Now, if we reorganize this sigma b, looking at this statement that we have already given, sigma b is equal to bending moment times d, which is the outer diameter, divided by 2i, according to, if I get m out of I equaling to sigma b divided by y, if we substitute d out of 2 in the place of y. So it means sigma b will equal to md divided by j. But we know that this j is coming from the fact that 2i is equal to j, or twice the moment, the second moment of area is equal to the polar second moment of area of that particular section. So having noticed that, we can now look at our formula of maximum shear stress according to the maximum shear stress theory or Tresca theory, that tau max, or the maximum shear stress, is equal to half of the square root of what we said, the bending moment squared plus 4 times the shear stress squared. But we have already discovered that this bending moment stress is equivalent to the bending moment times d divided by j plus 4 into, we know this tau has been computed from above as torque times diameter divided by twice the polar second moment of area, and the whole thing squared. So if it is a solid shaft, of course we have said that d to power 4 times pi out of 2 is equal to j. So if we substitute it in, we realize that tau max is equal to half square root of md divided by j. But j is now, when we substitute it in, it will be pi times d to power 4, and the 32 will go upwards, and this whole thing is squared, plus t times d, because we have substituted the j here, so it will be twice j, which will be pi d cubed. Pi d cubed, we take this 32 upwards here, and therefore we shall have our component here. This is actually d to power 4. This is d to power 4. So tau max is equal to a half square root of 32m divided by pi d cubed, because one of this d, this one here, is cancelled with the d to power 4, and it becomes d cubed. Then the whole thing squared plus 32 divided by pi d cubed, because we know this d here cancels with this 4 to get 3 here. So that becomes a half square root of 32 out of pi d cubed squared. If we factorize out this 32 out of pi d cubed, then it will be root of a half times root of 32 pi d cubed squared, then m squared plus t squared. So which will give us tau max equivalent to a half times 32 out of pi d cubed square root of bending moment squared plus the twisting moment torque. Now when we look at this kind of expression, this square root of m squared plus t squared is what we call the equivalent twisting moment. So that is the equivalent twisting moment, and it means if we take this 16 out of pi d cubed to cross the other side, it means pi d cubed out of 16 tau max is equal to square root of m squared plus t squared, which is the twisting moment Te. So if we limit the maximum shear stress to equal to the allowable working stress, it means this tau max will tend to tau, which is the allowable working shear stress. Therefore, if we substitute this tau max with tau, which is the allowable working shear stress, it means pi d cubed out of 16 times tau is equal to that. So it means this equivalent twisting moment Te equal to square root of m squared plus t squared is equal to pi d cubed divided by 16 times tau, and it is from here that we can calculate d. So we continue and consider another failure criterion, which is the maximum stress theory or the Rankines theory. So from the maximum normal stress or the maximum principal stress theory, we know that the maximum principal stress is equal to a half times the normal stress sigma b plus a half square root of normal stress sigma b squared plus 4 tau squared, or the shear stress squared. So it means if we substitute in our values, we shall have a half MD out of J plus a half square root of MD out of J squared plus 4 TD out of 2J squared. When we substitute in properly, we find that sigma B max, or the maximum normal stress or the maximum principal stress, times pi d cubed out of 32 is equal to m out of 2 plus a half square root of m squared plus t squared. It is therefore from here that we can also calculate the value of d. D can be calculated. So we compare it with the value of diameter obtained from above in the maximum shear stress theory, and if we find we compare the two, the one which is bigger is the one that we shall go with, and it is the one that will be able to withstand failure from both criterion. So in other words, a larger value of D is taken. Thank you so much.